Time to talk about another exam. This one is from multivariable calculus. Locally, it's called Math 265. A beautiful exam 2. So we're getting into sort of the differential aspects of multivariable calculus, and a wonderful vintage year too, fall 2023. Back in the wonderful days when there were 7 problems on an exam. So there's a lot for us to be looking forward to. We're going to have fun, but of course, as always, we need to start by putting down our name. Because if we don't get our name on there, we're not going to get the credit. And so, with that out of the way, let's begin. Number 1. Consider the function f of xyz is the natural log of 1 plus xyz. And we're asked to find the third derivative, so this symbol means it's a partial derivative, and the 3 says we're taking 3 derivatives, and we're going to take them with respect to x, then with respect to y, then with respect to z. Now, in some sense, order technically matters, but for most nice functions that we encounter, the kind that you see walking down the street any day of the week, order really doesn't matter. So the key is we're going to take derivative with respect to each variable. And we're going to leave our answer in this form, 1 plus a xyz over 1 plus xyz cubed, where a is a constant whose value should be found by you. Well, of course. Who else is going to find it if it's not us? Okay, all right. All right, and then there's this hint which just says, oh, you might recognize this notationally in a different way. So there's 2 ways to write partial derivatives. Okay. Now, in some sense, they were kind of nice to say, this is what your final answer should look like. So if it doesn't look like this at the end, we're going to know that we made mistakes. Or they wrote the problem wrong, but more likely we made mistakes. Because, of course, they always carefully check problems, right? Right? All right, well, let's get to work. So let's start, and I'm going to use the subscript notation just because it's a little bit easier for me to keep track. So we have our original function. So we'll start by writing that down. F is the natural log of 1 plus x, y, z. Or, if we're sounding fancy, z. Okay, so we'll start f sub x. Now that means we're taking the derivative with respect to x. And remember, as we take a derivative, one thing is going to vary, and the others are going to be constants. So when we talk about f sub x, that says, hey, the x is the varying part, and the y and z you treat as if they were numbers. Okay, so how do we take the derivative of a log? Well, the rule is you take 1 over, and whatever's on the inside, so 1 over 1 plus x, y, z, and then you times that by the derivative of the inside. Now remember, x is our variable, y, z we treat like constants, and derivative of 1 is 0, so we have like a constant x, so that derivative is y, z. Okay, which we can rewrite this as y, z over 1 plus x, y, z. All right, good, good. Okay, next layer. Now we're going to take our derivative with respect to y. So f, x, y. So we're going to come up to what we just found. Say, all right, now y is our variable, and the x's and the z's, they're the parts that we treat like constants. Now you notice we have y in 2 places. Yep, we've got y in 2 places. All right, so what do we need to do? We need to just make sure we follow the right rule. Now, what rule are we going to be needing here? Well, there's a couple rules we could do, but one rule we could do is the quotient rule, right? Because you have function on top with the variable, function on bottom with the variable. All right, quotient rule. So let's see if we can remember that. So how does that go? So the quotient rule says you take the bottom, so 1 plus x, y, z, times the derivative of the top. Now remember, the derivative of the top is with respect to y. It's that thing right there. Derivative of yz with respect to y is z. Okay, minus the top, yz, times the derivative of the bottom. Okay, again, the derivative with respect to y. So derivative of 1 is 0. and it's like constant y, so it's that constant xz. And all of that over the bottom term, 1 plus xyz squared. All right, let's clean this up. So what do we have? We have a z plus an xyz squared minus, we have an xyz squared, nice, over 1 plus xyz quantity squared. And why did I say nice? Well, you'll notice we have an xyz squared and a minus xyz squared, so they cancel. Oh, how lovely. How lovely. Okay, so catching up, we'll just write that as z over 1 plus xyz squared. Okay, good, good. Now, one more to go. So we've taken the derivative with respect to x, we've taken it with respect to y, now with respect to z. All right, well, let's see what's going to happen here. So we're going to have f x, y, z. And like in the previous case where we had y on top and bottom, now we have z on top and bottom. So again, quotient rule. So what do we have? It's going to be the bottom, 1 plus xyz quantity squared, times the root of the top with respect to z, which is 1, minus the top, z, times the root of the bottom with respect to z. So, okay, chain rule, 2, 1 plus xyz to the first power, times the derivative of 1 plus xyz with respect to z. Well, 1 is 0, and then it's like constant z, and so we end up with just the constant there, which is the xy. All of that over 1 plus xyz squared squared. Well, squared squared is another way of saying what? Well, that means to the fourth power. All right, cool. So let's do a little bit of simplifying here. So we just say, this part is like 1 plus xyz to the fourth. And what do you see? There's a 1 plus xyz, there's a 1 plus xyz squared, 1 plus xyz to the fourth. So what we can do is we can pull out 1 from the top and cancel with 1 on the bottom. So if we do that, what will happen is this will go away, this will become to the first power, and this will become cubed. All right, so let's see what's left at this point. Well, we have 1 plus xyz to the first, so that's a 1 plus xyz. And then here we have a minus 2zxy, right, because that's canceled. So minus 2, and then it doesn't matter which order we write it in. So that's again xyz. And then downstairs, it's 1 plus xyz cubed. And you have an xyz and a minus 2xyz, and they combine together, get 1 minus xyz over 1 plus xyz cubed. And ta-da! That's it. That's it. Now, let's make sure we answered the question just the way they wanted us to, right? Said, find this third derivative and leave your answer in the form 1 plus axyz over 1 plus xyz cubed. And they said, oh, we found it, and that's our answer. So when we put a box here, that wasn't a mistake. That box is right, because we're looking for the derivative, and we want to make sure it matches. You'll notice here, it does match, right? You get a 1, and then something xyz. So that says what? So this really is telling us that here, a is minus 1. I'll just make a little side note. That's really not part of the answer. It's sort of built into it. And wow, great. Wonderful, wonderful. So this one's kind of fun. It's taking 3 derivatives. A little bit interesting because quotient rule, wow, it's been a while since we've done that. But hey, you know, it's like riding a bike. You never forget. All right, well, on to the next problem. Number 2, find the equation in the form ax plus by plus cz equals d for the tangent plane to the surface described by the equation tangent of pi x minus 2xy plus e to the zx plus y squared z equals 3, and we're at the point 0, 1, 2. And determine the numbers a, b, c, and d. Now, on a side note, technically speaking, a, b, c, and d will not be unique, but we'll get to that in a moment. But we're among friends, so we know what this means. All right. So what's our setting? What do we need to be doing? Well, we know a couple of things. We know we're looking for a tangent plane, and we know we're looking for a tangent plane because it says tangent plane. All right. Well, that was a pretty good hint. But how do we find it? Now, generally speaking, there's two ways we talk about finding tangent planes. One scenario is when you have z is a function of x and y. And then the other scenario is when you have something like this. So, spoiler alert, we're in that other scenario. And you might say, well, what do you mean by you have something like this? Well, namely what it means is that you have a function, and I'll write it as a capital F of x, y, z equals a constant. I'll just put number here. All right. So this is our setting. So we're in a function equals a number. Now, this is actually the better one in some sense. Because if you are in this setting, then it turns out it's pretty straightforward. Now remember, what do you need to make a plane? Well, you need two pieces of information, a point and a normal vector. Okay, now this is our point. So here we go. There's our point. And when we're in this setting, it turns out that our normal vector can be described in the following way. Namely, it's our gradient of f at our point. So that's it. So great. So now we have a plan. So we know we're taking our function, we'll write it down again, f of x, y, z. It's equal to tangent pi x minus 2xy plus e to the xz plus y squared z. Okay, there's our function. Now we're going to take the gradient of that. Okay, and gradient is a wonderful tool. You should essentially think of the gradient as acting like derivatives. And so we're going to probably see the gradient again on this exam because, well, people like derivatives in calculus. It's one of their two favorite things in calculus, derivatives. The other one, integrals. We'll save that for another exam, though. All right, so we have our gradient. Now, what does the gradient look like? It's your partial derivatives. So we're going to take the partial with respect to x, a partial with respect to y, and a partial with respect to z. Okay, so here we go. So we're taking the derivative with respect to x, and so anything without x is a constant. Derivative of tangent, secant squared. All right, well that's cool. So it's secant squared pi x. And then don't forget chain rule, have to multiply by the root of the inside. So there's going to be a pi. The derivative of 2xy, well, is 2y, because x is the part that we're taking derivative with respect to. We're treating y like a constant. E to the xz, again, we'll do a chain rule. Derivative of exponential is, well, the exponential function. And then times by the root of the inside, which will be, in this case, c. And that part, there's no x. So, good. Now with respect to y, that's 0, no y. Here, minus 2x. Here, there's no y. Here, okay, derivative of y squared is 2y. So it'll be 2yz, right? Because z is acting like a constant. Last part, derivative with respect to z. 0, there's no z. 0, there's no z. Here, chain rule like we did before. So e to the xz times the root of the inside with respect to z, which will be x. And then derivative of y squared times z is y squared. All right, good, good. Okay, now what comes next? Well, we need to plug in the point. So the gradient of f at 0, 1, 2. Okay, so what do we get? Well, okay, so we can get pi secant squared of 0. What's secant of 0? It's 1. So think of cosine of 0. Cosine of 0 is 1. That one we're comfortable with. So secant, 1 over that. So cosine of 0 is 1. Secant of 0 is also 1. So we have a pi. Okay, cool, pi. Minus 2 times 1, so that's minus 2. And then plus 2 e to the 0. Because, you know, x is 0. Hard to recover from that. So plus 2, comma. Minus 2 times x, which is 0. 2 times y times e. 2 times 1 times 2 is 4. Then here we'll have x, e to the xc. Well, x is 0. Okay, so that's going to go away. And y squared is 1. Well, of course, we can simplify that. So that's our pi 4, 1. All right, and remember, that's our normal. So we've got our point, it was given to us. We've got our normal vector. We found it using the gradient, and their powers combined. They will give us what we need. All right, so that's as our plane looks like. Pi x plus 4y plus z equals something. And now, where did these numbers come from? Pi 4, 1? Well, they came from here. This is a, b, c. Now, how do we figure out what goes there? Well, we have our point. We plug it in. So we should have, well, pi times 0 plus 4 times 1 plus 2. So plugged in x equals 0, y equals 1, z equals 2. 0 plus 4 plus 2 makes 6. So there's our plane. So that says, hey, a should be pi, b should be 4, c should be 1, d should be 6. Now, why did I say this is not unique? Well, because you could actually multiply all of these by a number. 2 pi x plus 8y plus 2z equals 12. Same plane, same plane. And so, but from context, they just need one that works. And probably this is a pretty nice set of numbers. And so there we go. We found it. Woohoo! On to the next problem. Number 3. We're going to get to channel our inner artiste. Woohoo! So we're asked to do a sketch. Sketch the domain of this function. F of x, y is the square root of 2y plus x over log of y squared minus x. Use dashed lines to indicate, indicated. Oh, I think that's a typo. We'll forgive them, you know. It's not an English test. When the boundary is not included, solid lines to indicate including the boundary, and shade included regions. One set of axes has been provided for practice. Nothing above the dashed line will be graded. Okay, so we've got practice here. All right, good. Well, let's recall, we're talking about domain. So when we talk about domain, there's 3 things we've got to pay attention to. So what do we need? Well, we really say, what do we need to avoid? So they come in, as I said, groups of 3. So we can't have a square root of a negative. So square roots only make sense when the inside is greater than or equal to 0. We cannot have a log of anything less than or equal to 0. So log is only defined for positive numbers. So log of a positive. Log of 0, undefined. Log of negative, undefined. Unless you're in a different class, but in our class, undefined. Okay. Then the last thing is we can't divide by 0. All right, so we have our 3 problem areas, and so we just need to go through and say, hey, what's going on with these 3? So let's start. So let's start with our first one. Okay, square root of a negative. Can't have that. Well, so we see, do we have a square root? And we do. All right. So we look inside the square root and say, all right, whatever is inside the square root has to be greater than or equal to 0. So we need 2y plus x greater than or equal to 0. Okay, well, that says what? Well, we can subtract. It says 2y greater than or equal to minus x, or y is greater than or equal to minus 1/2 x. So let's just start with the y equals. Y equals negative 1/2 x. That's a line, goes through the origin, down 1 over 2. So marking some points here, and now connect the dots. Solid line, because we have equality. And there we go. So y equals minus 1/2 x. Now y needs to be greater than or equal to minus 1/2 x. And so which side are we on? When in doubt, pick a point. Say here, x equals 0, y equals 1. Is 1 greater than or equal to 0? Yes. All right, cool. So what do we do? Well, we shade. So that says we want to shade everything that's on this side of the line. All right, so we get the whole thing there. All right, cool. We've already thrown out half the points, right? Because we have the points above and the points below. So progress. All right, so that takes care of this scenario. Now the square root problems are dealt with. Let's go to our log problems. So we need to make sure that what's inside our log is positive. Okay, so we say, all right, we need y squared minus x to be positive. Or y squared needs to be bigger than x. All right, well, what's going to happen here? Well, if we said y and x squared, y equals x squared, for instance, you'd say, oh, parabola, woo, smiley face, ah. What about x equals y squared? What do we say? We say, aha, parabola, woo, sideways opening parabola. And so yeah, it's the parabola just turned on its side. And so we can mark some points. Again, origin, and so it's a little hard to see the grid on this document camera, I suspect. But so there's a little grid here. So that's 1, 1. Here is 1 minus 1, and here 2, 4. And all right, so now we have our parabola, and goes like this. And I drew it as a solid line. That was a mistake, right? It should be a dotted line. So I'm gonna put a lot of dots here along the way. Using a lot of ink on this problem. That's all right. There we go. There's our dotted line. Now, okay, which part of the parabola are we in? Right? Because again, just like the line cut into two parts, this parabola cuts into two parts. Sort of like on the inside and on the outside. How do you know? Well, the answer is you pick. So let's pick a point. Let's say something over here, where x equals 2 and y equals 0. And we plug it in. X equals 2, y equals 0. Is 0 bigger than 2? Well, no. Well, that means we don't want to be on the inside. We want to be on the outside. And so we say, okay, great. Shade in the outside. So we start shading the outside. And well, there's a lot of outside. And there we go. Shoop. All right, good. Now, that takes care of our log scenario. All right, so let's mark that off as well. Boop. Okay, and then our last point. Well, what's our last point? Well, so our last point, or I should say our last problem, not our last point, division by 0. So we do have a fraction, so we have a possibility of dividing by 0. So we say, all right, well, we need log of y squared minus x. That can't be 0. Well, when does log of something equal 0? Well, the answer is when the something is 1. So we need y squared minus x to not be 1. All right, well that says, I'll move it around, so that says y squared minus 1 cannot be x. Okay, so what's happened? Well, we had x and y squared, and that was the parabola. Here we have x and y squared minus 1. So it's also a parabola, but now it's shifted. And you have to sort of ponder for a moment, what does it look like? And how did it shift? You know, because there's different ways it could shift. And here we say, oh, well, x, you basically are subtracting 1 from all the x values. So subtracting 1 from all the x values means that you shifted to the left. And so it's this parabola here, but just shifted over by 1. Okay, so there we go. All right, so we have to avoid these points as well. Now, the hard part. Where do all these things come together? Okay, now some things are easier to spot than others. All right, so let's talk about the parts which are easier to spot. You have all this stuff up here. This is good. We like this part. And you have essentially this piece. But notice this little sliver. It barely fits in, but you'll see it's above the line, outside the parabola. Oh, they're sneaky. They're so sneaky. But that's also in as well. But of course, down here, no. And over here, no. We're just not going to work for us. Okay. All right. Good. Good. So now let's start drawing. And we're going to be careful here. All right. So let's work on this piece up here first. Well, the origin is out. It's on a dotted line. So I'll put a little circle here. And then there's another point low over here. So, well, I'm going to quickly try to sketch this line, but keep in mind that there's a point nearby that's out. And there we go. So we're missing a point there. And all right, now we have our parabola, dotted line. So there's our parabola there. And then we have another parabola here. And coming across. And then everything else is okay. So in between is okay. Above is okay. And there we go. All right. So that's part of it. And in addition, okay, what else? Well, here, what's happening? Well, okay, let's see. We can eyeball this in. Yeah, that's not the easiest thing to eyeball in, is it? Roughly right around there. And then we have a solid line. And then we have this parabola, dotted line. And we have another parabola sweeping through. We can barely catch. All right, just that sliver. Ah, my goodness, that's throwing us for our game. So there we go. Then that's part there. So there's our domain. Wow. Huh. Well, that's an interesting picture. All right. Well, okay. Cool. What's the moral here? Be careful. There might be a little sliver hiding. So hopefully our pictures don't have to be quite so interesting. Maybe be blessed to have non-interesting problems. All right. Well, that's problem 3. Let's keep going. Number 4. Find the second order Taylor polynomial of a function, x cubed y minus x plus y squared. That's a pretty nice looking function. Polynomial, one of our favorite kinds of functions. And we're at a particular point. xy equals 1, 0. Okay, so let's recall what Taylor polynomials are. The goal of Taylor polynomials is to say, hey, we want to get an approximation to our function by a polynomial. Now, it's okay that we're starting with a polynomial and approximating it with the polynomial. Ultimately, the goal is to say, I want to make sure my derivatives are matching up to a certain point. Okay, so how does it look? Well, if we're near a point a comma b, so in our case, 1, 0, this is our a comma b. Then what we say is that our function, f of xy, well, it looks like a couple things together. It's f a b, so that says I want the value of the function to match the polynomial. And then you add in the first derivatives, fx a b, x minus a, plus fy a b, y minus b. And if we stopped here at just these two, we'd have the tangent plane. So the tangent plane, it's a Taylor polynomial. But we're going for second order. Now that means we want second derivatives. So the last stage here, 1/2 fxx ab, x minus a squared, plus fxy ab, x minus a, y minus b, plus 1/2, fyy ab, y minus b squared. Now, there's a couple of things you'll notice here. For example, yy, there's two y pieces. xy, there's an x and a y. And they might say, well, where are these halves coming from? Well, think about taking derivatives. When you take a derivative here, a 2 comes down, and you need to compensate for that 2 coming down. So that's why there's a half. So how does one find it? So once you understand the generic formula, the way we find it is we find all these partial derivatives. So time for us to take a lot of partial derivatives. All right, so now we just have to be very patient with ourselves. fxy, and the good news is these are nice functions, so we won't stress too much. So we have to take the first derivatives, fx sub xy. We're treating x as our variable and y as our constant, 3x squared y minus 1. Fy of xy. All right, now y is our variable, and x is like a constant. So you get x cubed plus 2y. Fxx, xy, okay, find f sub x, take the derivative of that with respect to x again, and we'll get 6xy. Fxy, xy, well, okay, go to f sub x, take the derivative of that with respect to y. And what do we get? 3x squared. Now, fun check, go to f sub y, take the derivative of that with respect to x, you should get the same thing. And we do. Nice, 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 nice. And one more, fyy of xy. Okay, go to fy, take the derivative again with respect to y, and we get 2. Okay, now, these are not what we plug in. Because notice, these are all evaluated. These are numbers. So now, after we found the partial derivatives, the next thing is plug in. Okay, so here we go. So we're plugging in 1, 0. So everywhere where you see an x, you put a 1. Everywhere you see a y, you put a 0. Now, because 0 is a wonderful friend, anything with a y is automatically 0. So you'll notice here, y term goes away. We're left with minus 1. Fx 1, 0, there's a y, so we're left with minus 1. Fy of 1, 0, there's a y there, so we're left with 1 cubed, which is 1. Fxx at 1, 0, well, there's a y term, so that's just all out. fxy at 1, 0. Okay, there's no y, so it's 3 times 1 squared, which is 3. fyy at 1, 0 is just the number 2. All right, great. So what's going to happen is we're going to plug in. So what do we have? We have that f of xy is approximately, and we'll go through these term by term. So the function, minus 1. Now we have f sub x, which is minus 1, times x minus a, x minus 1. F sub y at 1, 0, which is 1, so plus 1 times y minus 0. Okay, so that's that, plus 1/2 fxx, which is 0. Okay, so that whole term is gone. Then we have plus fxy at ab, so fxy at 1, 0 is 3, so plus 3 times x minus 1, y minus 0, plus 1/2 fyy at ab, which is 2, times y minus 0 squared. And we can clean this up. Say, okay, so that's minus 1, subtract x minus 1, add what y is, add 3 times x minus 1 times y, and 1/2 times 2 makes 1, so add y squared. And there we go. There is our second order Taylor polynomial. Nice. Now, you might say, shouldn't we expand? No, don't. Resist the urge to expand. It's the same expression, true, but in terms of applications, and we notice that there's a little bit of a question here. So if you're going to do anything with your second order Taylor polynomial, you want to leave it in the x minus a, y minus b type form. Don't expand. All right, on to part B. Okay, use, our application, the second order Taylor polynomial to approximate f of 1.1, negative 0.1. And so we've done all the hard work in part A. What's left? Well, we're plugging in. So we know f of 1.1 comma negative 0.1. And the key here is that this is close to 1 comma 0. So that's why this is a reasonable approximation. So it's minus 1, subtract 1.1 minus 1, plus negative 0.1, plus 3, 1.1, subtract 1, times negative 0.1, plus negative 0.1 squared. So we're plugging in for our x's and y's. Okay, so what do we have? So this is minus 1, subtract, 1.1 subtract 1 is 0.1. Then we have subtract 0.1. 1.1 subtract 1 is 0.1 times a 0.1. That's like 1/10 times a tenth, which is 1 over 100, or 0.01 times a 3. And now check the sign, positive, positive, negative. So it's subtract 0.03. Then we're going to add negative 0.1 squared. Well, the negative will go away because you squared it. 0.1 times 0.1 is 0.01. So plus 0.01. Now, quick note, this is negative 0.02, and we have lots of negatives. So lots of negatives are actually good. If everything's negative, well, think of them as all positive, and then it's easy to do the math in your head and throw a negative in at the end. So 1 and a 0.1 and a 0.1 would have to get us up to 1.2 and a 1.22. And now, don't forget, there's a negative in the front. So negative 1.22. And that's our answer. Nice, nice. And, well, there we go. Life is good. And, yeah, this isn't terrible, right? We just have to remember the form. And yeah, there's a lot of things to write down, but lots of pieces in motion. Be patient, take your time, get the right form. Life is good. Let's keep moving on. Number 5. Find all coordinates and the values of the absolute maximum and absolute minimum of the function 2x squared minus 4xy plus 4y squared minus 2x over the triangular region with vertices at 0, 0, 2, 0, and 2, 2. Okay, so let's start by talking about this region. And so we'll do a quick sketch. We have corners, and our corners are 0, 0, which would be here, 2, 0, so x equals 2, y equals 0, so that's there, and 2, 2, which is here. So we have this triangle. Now, it's a triangular region, so it's not just the outside, it's the inside as well. So, okay, so we have our region here. All right. So, now, 3 vertices. Okay, what do we do? How do we approach this problem? Well, this is our making a list. We're making a list, checking it twice, gonna find out which points are nice. Exactly, right? So what's our list? It's a list of all the places that we think it could happen. So how do we go about making our list? Well, the first thing I do is I always start by throwing in the corners, because corners are always candidates. So we have the 3 points, 0, 0, 2, 0, 2, 2. All right, what comes next? Well, let's talk about the inside. Now, if we're looking for the inside, well, that says we're looking for a place where we have a local min or a local max. So that's the place in particular where on the inside, we're going to search for the gradient equals 0. Okay, so let's do that. And all right, so what do we have? Well, we'll have our f sub x is 4x minus 4y minus 2 equals 0. Okay, taking derivative with respect to x, and we're setting it to 0. And f sub y, well, that's minus 4x plus 8y, and that equals 0. All right, well, if we quickly add these together, you see the 4x's cancel, and then what do we get? We get minus 4y plus 8y, that's 4y, and minus 2 equals 0, which says y should equal a half. And now that we have y equals a half, well, we can plug it in. Minus 4x plus 8 times a half, which is 4, equals 0, or you rearrange, x equals 1. So for the inside, we get the point 1 comma a half. Now, I wrote it down, but I should have done something first. Before writing it down, what should I have done? I should have asked myself the question, do I care? Now, I actually knew I cared. That's why I was so quick and cavalier. But how do we know? Well, we have to check and say, is it part of our region? So if it had been over here, nonsense. Throw it out. Don't even consider it anymore. But 1 a half is right there. And that is part of our region. So we do have to consider it. Okay, so that makes our list. Well, what else do we need? We need to look on the edges, the boundary. And we've got 3 boundary pieces. So we're going to be doing a lot of this. So, all right, let's start. Let's start with our bottom part. And what's true about points along the bottom here? On the bottom, we get that y equals 0. so that our function f of xy becomes f of x0. Well, okay, so that's 2x squared and minus 0 plus 0 minus 2x. And notice this is a function of one variable, so we can take the derivative. The derivative would be 4x minus 2. So think of this as just a new function g of x. G prime of x equals 4x minus 2, set that equal to 0. That leads us to x equals a half. So what does that say? Well, that says on this bottom border, we're interested in x equals a half, which is a point. So we have to add it to our list. 1/2, 0. Okay, so that's good. What's another boundary that we have? So that's the bottom. Let's do the one that's at an angled boundary, the one that's on this bit of a slant here. All right, we'll do our angled side. And what is that? Well, that's y equals x, right? And so we can really think of this as f of x comma x. So, well, okay, so that says everything is an x. So you have 2x squared minus 4x squared plus 4x squared and minus 2x. And what do you see? It looks like 2x squared minus 2x. And now at this point, you're like, aha, we've played this game before. Take a derivative, g prime, set it equal to 0. You get x equals a half, which says that at this point, 1/2, 1/2 is also a point we care about. And notice it truly is on the boundary. If we'd gone something down here, we'd say, who cares about that point? But we care about this point, 1/2, 1/2. Okay, great. So that's that side. All right. We're running out of space, and we're not running out of sides. Well, we're almost out of sides. Okay. You know, the end is in sight. All right. We'll call this one the right-hand side. Now, what's true about the right-hand side? Well, on the right-hand side, all x values are 2. So that says x equals 2. And let's see. All right, I want to make sure we can see f while we do this. So our f of 2 comma y looks like, okay, so that's 2 times 2 squared, which is 8, minus 4 times 2 times y, that's 8y. 4y squared, that's 4y squared. And then minus 2 times 2, that's a minus 4. Okay, so this is the same as 4y squared minus 8y plus 4. All right, now, we're thinking this as a function. I'll call it g of y. I know I've used g in several places, but it's just a temporary placeholder. Take our derivative, g prime of y. We get 8y minus 8, set that equal to 0. You end up with y equals 1. So that gives us a point here. And so, okay, wonderful. So that says what? It's at 2 comma 1. Because we're on x equals 2, and we found y equals 1. All right, so there we go. There's our last boundary point. So we had the corners, we had the inside, and then we had our 3 sides, and we've made a list. Whew. All right. Now, we check it twice, and check and just make sure to include all possibilities. Corners, edges, inside. Yes, we got all those. All right, good. Now, what do we know? We know that our answer for the absolute max and absolute min occurs on our list at one of these points. How do we figure it out? Well, the answer is we plug in. Okay, so each one of these, we're now going to plug in, and we're going to see what comes out. Now, some of these will be easier to plug in than others. And so, for example, 0, 0, 0, 0, 0, 0. Ah, that's lovely. And, well, it's going to go up in difficulty from there. Okay, so let's try a few of these. So x equals 2, y equals 0. Now, we could plug it into here. We could also say, oh, at x equals 2, y equals 0, we're on the bottom. And we could plug it in for x equals 2 here. Well, that's 2 times 2 squared, which is 8, minus 2 times 2. So that's 8 minus 4, that's 4. All right? Since we have these pieces for the sides, use them. 2, 2. Well, that's on our angled side. And so we say, okay, so we can again plug it in. And everybody see x, put 2. 2 times 2 squared minus 2 times 2. So that's 8 minus 4, which is equal to 4. All right, good, good. All right, well, 1/2. Well, that's not on any side, so we actually have to do that one properly. So let's be careful here. Okay, so 1/2, so that's 2 times 1 squared, which is 2. 4 times 1 times 1/2. 4 times 1 times 1/2 is 2, and we're subtracting that. 2 minus 2. 4 times 1/2 squared. Well, 1/2 squared is 1/4 times 4. 4 times 1/4 is 1, so we add 1. Then we subtract 2 times 1, and so that's minus 2. 2 minus 2 is 0, plus 1 is 1, minus 2 is minus 1. Okay, now 1/2, 0. All right, well, that's on our bottom. And so we can come here and say 1/2, 0. So that's 2 times 1/2 squared. Well, okay, that's going to be 1/2 minus 2 times 1/2, which is minus 1. That's minus 1/2. 1/2, 1/2. Okay, that's like our angled side. So that's 2 times 1/2 squared, okay, which is 1/2, minus 2 times 1/2, minus 1. That's minus 1/2. All right, great. 2, 1. That's our right-hand side. Okay, so we can come here, say, plug in y equals 1. So that's 4 times 1 squared, which is 4, minus 8 times 1, minus 8, plus 4. All right, 4 minus 8 plus 4 is 0. Great, wonderful, wonderful. Okay, so we've made our list. We plugged it all in. Our last step is the answer. So we're looking for absolute max and absolute min. For the absolute max, we look at these numbers, 0, 4, 4, minus 1, minus 1/2, minus 1/2, 0. What's the largest number? 4. So 4, these are our absolute max. Now, absolute min, again, look at the same numbers. What's the smallest number? Minus 1. This is our absolute min. And so we can say absolute max of 4 at 2 places, 2, 0, and 2, 2. So in other words, we hit our max at these corners. Absolute min of minus 1 at, and that's at 1, 1/2, which is this point on the inside. And that is our answer. We'll put little arrows so that the person grading it knows, because there's a lot of work here. They say, aha, yes, I see where the answer is. Good, good, good. All right, well, there we go. Okay, so this is always an interesting one, but the process is not so bad. Make a list, corners, edges, inside, make sure you account for all those things on your list, plug in the points, and read off max and mins. So there we go. Ah, wow, what a fun problem. but let's keep going. Number 6, find the maximum and minimum values of 4x minus y subject to the constraint f of xy is 2x squared plus y squared equals 36. Show all the work. So we're showing all of the work. Now there's various ways to do this, but really we're thinking of this problem as the category of constrained optimization. So why do we say optimization? Well, because we see words like max and min. So that means we're trying to optimize. Where's the constrained part coming from? The constrained part says, hey, there's this relationship going on. This 2x squared plus y squared equals 36. So it's not over all possible numbers. It's over all possible numbers that satisfy this. And so we say, oh, okay, so 2x squared plus y squared equals 36. All right, well, what do we do? Well, what we can say is there's this rule. This is a Lagrange multipliers. So we channel our inner Lagrange. Lagrange. Now, what does that say? So for Lagrange multipliers, what we have is that at the optimum, there's no desire for us to move. And that translates into saying that when we compare the gradients of the two functions, g and f, that they're multiples of one another. That's where the multiplier comes from, is this lambda. Okay, so how do we use that? Well, let's go ahead and set this up. So this is really going to give us a system of equations. And from that, we're going to learn information. Okay, so what are our equations? So what do we have? G sub x equals lambda f sub x, which becomes 4 equals lambda times 4x. And g sub y equals lambda f sub y. Well, that becomes minus 1 is equal to lambda f sub y is 2y. All right, good, good, progress. Now, what does this help us do? Well, what we can do is we can use this to figure out a relationship. So there's a mantra I like to use, which says, when in doubt, solve for lambda. And why? Well, it works really well. So here, what would we have? We'd have from the first equation, lambda would be 4 over 4x. In the second equation, we'd have minus 1 over 2y. Well, both of these are lambda, and so therefore, they're both equal to each other. This tells us that 8y is equal to minus 4x, or if you like, you can solve, says, oh, y is minus a half x. All right, well, that's information. Now, here, we've gotten a relationship between x and y. So that's really what we're doing here, is when we're solving this gradient g equals lambda gradient of f, we're really after a relationship between x and y. Now, how do we use that? Well, we say we actually had a relationship between an x and y already. And we say, oh, okay, well, let's combine them. Now, what was our relationship? It was our constraint. So we now have that 2x squared plus y squared needs to equal 36, and that y needs to equal minus a half x. All right, well, now we have two equations and two unknowns. So we solve. And there's, of course, many ways that we could solve this. And all right, let's replace y by minus a half x. And we could also say x equals minus 2y and replace x by minus 2y. But either way, we'll end up in the same place. So 2x squared plus minus a half x squared equals 36. Well, this is the same as 2x squared plus a quarter x squared equals 36. If you add 2 and a quarter, because they both are attached to x squared, this is 8 quarters plus a quarter makes 9 quarters. X squared equals 36. And then we move it across. That says x squared equals 36 times 4/9. So multiply by the reciprocal. And we're in luck. 9 divides into 36. And so what's left over is you'll have 4 times 4, which is 16. So that's x squared. So what is x? Well, square root of 16 plus or minus. So plus minus 4. So we get a pair of points. So we have again, we get a list. So these are all the points which satisfy gradient g equals lambda gradient of f. And there's a second constraint, which of course is that f equals our constant. So we found there's 2 points. Here we have x is 4, and remember y is minus a half x, so negative 2. X is negative 4, and y is minus a half that, so that's positive 2. So when we deal with our constraint optimization, it's saying these are interesting points you should look at. Now there's some interesting technicalities, and I will say it has happened multiple times in the past on exams which involve these constraint optimization, these Lagrange multiplier problems, that the people who wrote the problem did not pay attention and that the max and mins were not on these lists. But the reason that that happened is because our constraint was not bounded. Here, it's an ellipse. This curve, 2x squared plus y squared equals 36, is an ellipse. So we know it has, it attains a max and a min. And so just assume that for sure what we're after is on our list. Okay, now that we have that, we say, okay, what do we do with this? We plug in. So plug into not our constraint, but our function. So now we're going to look at g. Well, okay, we're going to get 4 times 4 minus minus 2. And here we're going to get 4 times negative 4 and subtract 2. Well, that says what? We have 18 and negative 18. So we have max of 18. And we'll just make a side note. 4, negative 2, min of negative 18 at negative 4 and positive 2. And that's our answer. We were after the max and min, and there we go. There we go. So recap, what goes on with these problems? We first off recognize what type of problem it is. We have something we're trying to optimize with a constraint. So we say, all right, we have gradient of g equals lambda gradient of f. We use that, using when in doubt, solve for lambda, to derive a relationship between x and y. We combine this relationship with our constraint to solve for our points. The points we're interested in are on the list, and we plug all these points on the list into what we're trying to optimize. And we'll just assume, we'll go off good faith that they gave us a problem where this is true, that the largest value is the max and the smallest value is the min. That's our procedure. Good. All right. Still a little bit more to go, so let's go ahead and finish it up. Number 7, our final problem. So we have this function f, which is a function of uv. It's a smooth function. Smooth is just another way of saying we can take derivatives. And we have that the gradient of f at 9, 2 is 1 minus 1. And g of xy is f 5x minus y, comma, xy. And we're asked to find the gradient of g at 2, comma, 1. Okay. Let's start unwrapping this. So what's going on here? Well, we don't have an explicit function for f, and we don't have an explicit function for g, really, because of that. So what do we need to do? Well, we need to use the data that we have. And so what we'll do is we'll think about, okay, what's our scenario? And, well, we have the following. We say, look, we have our g of xy is f of 5x minus y xy. So in some sense what we can think of it as really we have this f, which depends on u and v. And now u and v are going to become functions of x and y. Now you might say, oh, I see where you're going with this, Steve. You're going chain rule. Yes, this is chain rule. Now why do we think chain rule? Because we have functions inside function, right? Function says chain rule. So here we're thinking explicitly u is 5x minus y, and then v is xy. Okay, so what's going on? Why are we doing all of this? Well, the reason we're doing all of this is to say we're after our gradient of g. How do we do that? Well, technically the gradient of g at 2, 1, well, that would be the vector, which is fx 2, 1. Sorry about that. I got ahead of myself. G sub x 2, 1, g sub y 2, 1. Right? You take the partial derivatives and plug them in. So we need to understand g. Well, g we understand by this tree. So how do we take g sub x? Well, from the tree, we say, hey, g sub x would be f sub u, u sub x, plus f sub v, v sub x. So we see our x's here, and we go down our tree to get to those x's. So here, f sub u, u sub x, f sub v, v sub x. We'll come back and fill in some details here. G sub y, similar, is f sub u, u sub y, f sub v, v sub y. It's, again, same idea. We see some y's, and they're here. And we go down the tree to get to the y's. All right, good. Now, we start thinking, do we know anything? Yeah, we know a lot of things. We know what u sub x is, and so we say, okay, let's go ahead and replace what we know. So u sub x is 5, and v sub x is y, u sub y is -1, and v sub y is x. All right, cool. So, all right, so we have, this says 5 f sub u plus y f sub v. Here we have minus f sub u plus x f sub v. Now, we're almost there. What do we need to do? Well, we need to plug in 2, 1. So, when we plug in 2, 1, you might notice something. What happens when you plug 2, 1? So, at x equals 2, y equals 1, then u is 5 times 2 is 10 minus 1, which is 9. And then x times y is 2. So u equals 9, u equals 9, and v equals 2, which is right there. Ha 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 ha. Okay, all right, so we're almost there. We have to piece all our things together. And at this point, you're probably like, this is all you've completely smashed. But no, we've got our ideas. We know how to find the gradients. It's these partial derivatives. Because the function is a chain of functions. Functions inside a larger function, we use the chain rule to figure these out. And so we say, hey, look, g sub x at 2, 1 would be 5 f sub u, and now we say at uv, because f is a function of uv, at uv is 9, 2. Okay, plus y, well, y is 1, so plus 1 f sub v, 9, 2. Similar, g sub y of 2, 1 is what? Well, it's minus f sub u at 9, 2 plus x, which is 2, so plus 2 f sub v at 9, 2. Okay, now you would think that we're stuck. Do we know what fu and fv are at 9, 2? We do, because they told us. So this 1, that's f sub u at 9, 2, and this minus 1, that's f sub v at 9, 2. So we have that this is 5 times 1 plus 1 times negative 1. Our 5 minus 1, also known as 4. Then we have minus f sub u, which is 1, so minus 1 plus 2 times negative 1, which is minus 3. So our final answer, and we'll just ponder this for a second here, is that this is the gradient of g at 2, 1 is 4, negative 3. All right. Okay, so some unwrapping we should do. Let's try to recap this one, because this is one I think deserves a bit of a recap. So we're interested in a function g, which is built off a function f. We have some information about f. Namely, we know what its gradient is at a single point. And this is not just a random point, because if you look here, this 5x minus y xy at the point 2, 1, well, is 9, 2. So we're told essentially some partial derivatives at 9, 2. Now you might say, how do you know this is f sub u and that's f sub v and not the other way around? Well, here's where we get into conventions. Notice how we have an order here. First variable, second variable. So when we do gradient, it's the first variable, comma, second variable. So that's why it's fu, f sub v. All right, great. And so we see, because we have function, in function, chain rule. This is a chain rule problem. Chain rule problem, draw the tree. And say, all right, we can say, if I want g sub x, I have to work my way down the tree and to all the x's. Well, there's 2 x's. And similarly, there's 2 y's. And, well, because we know these inner pieces, we can replace them by what they are. And now evaluate. Okay. Lots of things to think about. Take your time. Don't rush. Take your time. Enjoy the process, right? We should enjoy it. Math is meant to be enjoyed. Part B. Let w be the unit vector in the direction in which g of xy increases the fastest at xy equals 2, 1. Find w and the rate of change of g at the point 2, 1 in the direction w. Now, this has a lot to do with the previous problem. What did we find in the previous problem? We found the gradient. So what are we being tested on here? Well, this is properties of the gradient. So this is not a chain rule problem anymore. This is like, hey, do you understand the thing you just found? What does a gradient tell you? The answer is that the gradient tells you how the function wants to go. It points uphill, and it points in the direction that's most steep uphill, if you like. And so when we talk about the direction in which it increases the fastest, that's the direction of the gradient. How much does it increase in that direction? That's the magnitude of the gradient. So what we have is that our vector that we're after, which is called this w, that's our gradient of g, 2, 1, over the magnitude of the gradient of g. Now, why that? Because it needs to be a unit vector. Okay, well, here we can find the magnitude pretty easy. That's the square root of 16 plus 9, right? Square the first entry, square the second entry, times our 4, negative 3. Well, they chose nice numbers. 16 plus 9 is 25. Square root of 25 is a fifth. So this is 1/5, 4, negative 3. So that's our W. And our magnitude, so rate of change equals the magnitude of the gradient, and that equals to 5, because that's the property of the gradient. All right, and so there we go. There's our W, and there's the rate of change. All right. Whew, good. After part A, part B was a nice cool down, right? Okay, well, what a test, right? Yeah, oh, it really was a test. It tested us. But that's all right. We got through it, and we were able to figure it out. You can do these things. Trust in yourself. Put in the time, study, be ready, and you'll be fine. You'll be great. I hope you have a wonderful time, and I hope I get to see you again. Bye.